Hello students, let us discuss positive displacement pumps. The main function of a pump is to move a fluid from lower elevation to higher elevation, from lower pressure to higher pressure, with higher flow rates. Vapor pressure of a liquid is the equilibrium pressure of a vapor above its liquid, that is, the pressure of the vapor resulting from evaporation of a liquid above a sample of liquid. Higher the vapor pressure, the more readily the liquid vaporizes. To keep liquid at the pump from vaporizing, the absolute suction pressure must be higher than the liquid's vapor pressure at that temperature. Pumps may be classified as rotodynamic pumps and positive displacement pumps. Centrifugal pump is an example for rotodynamic pumps. Positive displacement pumps can be further classified as rotary pumps and reciprocating pumps. In the current experiment, only the positive displacement pumps are discussed. A positive displacement pump makes a fluid move by trapping a fixed amount and forcing or displacing that trapped volume into the discharge pipe. Some positive displacement pumps use an expanding cavity on the suction side and a decreasing cavity on the discharge side. Positive displacement pumps can be both rotary and reciprocating type. Gear pump, lobe pump, vane pump, etc. are examples of rotary type positive displacement pumps. Piston pump, plunger pump and diaphragm pump are examples for positive displacement pumps. The gear pump has a drive gear and an idler gear. The shaft drives the drive gear and the drive gear drives the idler gear. In the gear pump, drive is transmitted from prime mover through suitable arrangement to the driver gear. The driven gear, which is in mesh with the driver gear, also rotates. At the suction side, the gears unmesh, allowing the fluid to get trapped between teeth and the casing. At the discharge side, the gears mesh back and forces the liquid out with high pressure. An application for the gear pump is fuel injection in a diesel engine. The driven and driver gears along with the casing are clearly seen. Common gear pump applications include various fuel oils and lube oils, chemical additive and polymer metering, industrial and mobile hydraulic applications, acids and caustic, low volume transfer or application. In a vane pump, vanes slide in and out of a rotor mounted off-center in the casing. Fluid is trapped between two vanes and the casing. Multiple ports permit the pump to operate through a higher pressure difference with less load wear on the bearings. Application areas of vane pump are aerosol and propellants, aviation and auto industry, fuels, lubes, refrigeration coolants and bulk transfer of LPG, ammonia and refrigerants, LPG cylinder filling, solvents and aqueous solutions. In a lobe pump, the rotors are mounted on separate shafts and rotate in opposite directions. The lobe pump operation is similar to gear pump. Instead of the gears, multiple lobes are used. The lobes are fitted with packing strips. Few application areas of a lobe pump are polymers, paper coatings, soaps and surfactants, paints and dyes, rubber and adhesives, pharmaceuticals and food applications. In a reciprocating pump, rotary motion is converted to linear displacement of a piston-like arrangement. In a suction stroke, the piston moves from the top dead center to the bottom dead center. Suction is created inside the cylinder, allowing the fluid to enter. During the discharge stroke, the piston applies pressure on the fluid, forcing the fluid out of the cylinder with high pressure. Main classification of reciprocating pump are piston pump and diaphragm pump. In a piston pump, a piston is fitted inside a cylinder which is designed to push the liquid with high pressure. Piston rings avoid any leakage of fluid towards the crank end of the pump. In a diaphragm pump, a plunger is connected to a sealed diaphragm. With the movement of the plunger, the diaphragm also moves, thereby creating sufficient suction. Fluid leakage from the diaphragm is avoided. Best suitable for corrosive, toxic and flammable fluids. The main application areas of reciprocating pump are oil and gas industries and petrochemical refineries, power plants, water treatment plants, refrigeration and cryogenic applications. At MSR UAS laboratory, a gear pump and a reciprocating pump test rig is installed to analyze the performance of rotary and reciprocating type positive displacement pumps. To analyze the performance of both the pumps, electrical power, shaft power, discharge along with the suction and discharge heads are to be calculated. The hydraulic power output to the pump is then calculated using discharge and total head. The pump efficiency can be calculated as the ratio of hydraulic power output to the shaft power input to the pump. A graph of total head versus discharge and efficiency versus discharge is also plotted. As experiments on centrifugal as well as reciprocating pumps are completed, it is important to know the differences between both the pumps. A centrifugal pump is mainly used for higher discharge, whereas a reciprocating pump is used for high head. In a centrifugal pump, priming is always necessary, but in a reciprocating pump, there is very high suction created at the inlet and hence priming is not required. Discharge in a centrifugal pump is continuous and smooth, but in a reciprocating pump, the discharge is intermittent and fluctuating. Centrifugal pump can handle large quantity of liquid, but reciprocating pump can handle small quantities. Centrifugal pump has less wear and tear and thus less maintenance. However, in a reciprocating pump, there are a lot of moving parts and hence it demands high maintenance. Centrifugal pump can thus run at high speeds, but the reciprocating pump is limited to low speed application. Cost of a centrifugal pump is less when compared to reciprocating pump, which is about 3 times the cost of centrifugal pump for the same power output.
Hello everyone. This is the setup to calculate the efficiency of a reciprocating pump test rig. As we all know that reciprocating pump is a type of a positive displacement pump. This is the second type of the positive displacement pump here at our MSR US laboratory. The first one, as we have already seen, is a gear pump, and here we are having a piston pump that reciprocates and thereby increases the fluid pressure of the fluid. The setup consists of a storage tank. Here we are storing water which will be used as the working fluid inside the reciprocating pump. From the storage tank we have a suction line the bottom edge of the suction line we have a foot valve in order to avoid the backflow of the water back into the tank. On the suction line we also have a suction valve which should always be in the open condition. Further, it goes into the pump. This is the reciprocating pump. It is a horizontal axis pump. The reciprocation action happens in the horizontal direction. The discharge of the fluid comes out through the discharge line over here. On the discharge line, we also have a delivery valve through which we can control the flow rate of the water. After the delivery valve, the water flows into the collecting tank. The discharge of the water flowing in the circuit can be calculated using the collecting tank. By closing the valve of the collecting tank, we can note down the time required for certain amount of the rise in the water level inside the collecting tank. The pump is being driven by an electric motor, also fitted with a V-belt drive. We are having a stepped cone pulley arrangement in order to change the speeds of the pump. On the panel of the test rig, we have a speed indicator which indicates the speed of the shaft of the pump. Also, we have a suction pressure gauge which indicates the suction pressure in millimeters of mercury. The discharge pressure or the delivery pressure of the water can be seen over here on the board-on gauge. Here, the pressure is measured in terms of kg per centimeter square. The power consumption of the motor can be calculated using the energy meter. Here, we have to note down the time required for a certain number of blinks on the energy meter, and using that we can calculate the power consumption. Now, let us go ahead and start the experiment. Before starting the experiment, we have to ensure that the suction valve and the delivery valve for the pump is always completely open, and we have to switch on the ECB trigger which is present at the back of the setup. Now we can see that the mains has come on. In order to switch on the main console of the panel, we have to turn the switch. Now let us start the pump. Now once the pump is switched on, we can see the speed of the pump here on the speed indicator of around 500 rpm. The suction pressure for the pump can be seen over here. It is showing of around 20 to 30 millimeters of mercury. The discharge pressure can be seen on the board-on gauge over here. The pressure is showing around 0.2 kg per centimeter square. The power consumption for the motor can be calculated using the energy meter. Here we have to note down the time for a certain amount of the number of blinks. Using the time and the number of blinks, we can calculate what is the power that is coming in to the pump. In order to calculate the actual discharge of the water flowing through the circuit, we make use of the collecting tank. First, we have to close the butterfly valve completely. After that, we have to note down the time for certain amount of the rise of the water in this piezometer. After the time is noted, we open the butterfly valve back. Now to take another set of readings, we can close the delivery valve, thereby increasing the pressure, the delivery pressure of the pump. Once all the readings for different delivery pressures have been taken, now we can go ahead and stop the pump. The same experiment can now be repeated for different speeds of the pump shaft. We know that the motor is driving the pump via a V-belt shaft. Now we shall change the speed of the pump by shifting the V-belt from this section to the next section. Now once the speed has been changed, we can repeat the same set of procedures for the different speed. We can observe that the speed of the shaft has reduced from 500 rpm to about 380 rpm. All the readings can be taken for three different speeds of the shaft, and we can calculate what is the efficiency of the reciprocating pump. Also, we can plot a head discharge curve.
At MSR UAS, we spark your imagination unlike any other.